Okay? And then we're going to see this drop because this, remember, as this thing is spinning, it's like generating a voltage that's fighting this one. Okay? So that's going to look like a voltage drop E. Okay, now suppose this system, you've applied 12 volts to the motor, right? And it takes a little time, spins up, now it's spinning. Constant speed. Okay, so if the thing's in steady state, we've got some current going in there, okay? And so this goes to 0, right? It's current constant, dIdt is 0. So what I'm going to be left with is V is going to be equal to IR plus that back EMF. Okay? Now if we substitute in for P, which we said is going to be proportional to the speed and that voltage back EMF constant, here's our relationship. Okay? Everyone okay with this so far? Kirchhoff's voltage laws go around the loop. Okay, so here's some questions. What happens as the motor speed increases? Okay, so suppose you start, at 0 speed. What happens as, if we have a constant voltage, right? When the speed increases, what happens to, like, the current? Okay. So if suppose omega 0, you have some value of I, right? V over R, right? Now what happens to that I as you start spinning up? Does it get bigger? It gets smaller, right? If this is constant, right? And I starts out as V over this, right? As omega starts spinning up, now I start getting a voltage here. This is constant. That means, and R is basically constant. That means this has to go down, doesn't it? I has to go down as we spin up. Okay, you see that? Yeah. So let's suppose we reach another constant speed and look at what is I. Okay. So basically, as that thing goes up, I goes down, right? So reach steady state speeds, right? Okay. So now, if I goes down, tell me about what's happening with the torque. Torque going up or going down? Torque, the ability to create torque at that speed is going down. Why? Because remember, torque was proportional to current. Okay? All right. So now, suppose omega reaches its maximum value for some given V. Okay? So what's I going to be? So I is basically going to be 0. Okay? Okay. And consequently, at that maximum speed, I0, no torque. Okay, so suppose the motor speed is 0, right? Suppose I'm applying a voltage, but I grab the shaft and I don't let it turn at all. Right? Rotor is locked. I'm applying that voltage. Okay? That's the largest current that I'll see through that motor. Because when it starts speeding up, that current starts going down. Okay, so I can find that current value, and then I can say, well, what's the torque at that value? Well, that's going to be the maximum torque, isn't it? Because that's the biggest current. And we said that torque was proportional to current through that motor, the torque constant, right? K of T. So, keep these concepts in mind. Let's take the next couple steps from that equation. We have this from the previous page. Now let's substitute for I, because we know for that motor that torque was equal to KT times I, or I is equal to torque divided by KT. So substitute that in for I. And you get this. Voltage is equal to torque over the torque constant times R times KE times omega. One more step. Let's solve for omega. And here's an equation that we're going to get. E over K sub E minus R over KT times KE times the torque. Okay, so now we have a relationship between speed and torque for the motor. And this is what it looks like if you plot it, right? As a function, if you're plotting speed versus torque, the slope, right, is multiplied times my independent variable torque, is a minus, so it's a linear downward slope, right? And this is the relationship. Okay, so there's a couple things to observe from this. First one is the intercepts with the speed axis. Okay, so where these lines intercept the speed axis, that has a special name, that speed. It's called the no-load speed. The no-load speed. Where do you get that? Well, at a zero torque, that's the speed that you're going to, right? That's the fastest speed that you're going to have for no-load speed. Okay, so that is a special value. And then the intercepts with the torque axis, right, over here, or depending on the voltage I'm applying, here, here, here. What speed is that at? Well, that's at zero speed. I grab the shaft, right? That's called the stall torque. Why? Because the rotor is stalled. It's not rotated. That's the maximum torque that you're going to get out of the motor for that applied voltage. Max. They'll have a little bit different kind of a torque speed profile, okay, but it's the same kind of idea applies. It's generally going to be the speed, the torque is going to kind of drop off the speed, but they'll be different, okay, depending on the construction of the motor.
I know that those motors, if they're in the wrong angle, they just won't step back. They just push back. But according to the
yeah, so if your motor were just one coil, you could have a problem. But look at that. There's a bunch of coils, right? So you will get some torque, okay? Kind of all the angle position. Yeah.
So obviously, with a power motor, you keep concerning the price. So is that
So long as you if you let it get too hot, it will do that. But if you cool it off,
is that the only reason why it goes? Because it's too hot.
okay, so basically what happens, and just like other electronic and electrical things, is you need to be careful about how hot things get. Okay, so usually you're probably not going to be operating at stall, right? Because usually you want to move something. So at stall, nothing's moving, right? So you're usually not going to operate there very long. Start up, right? Or something changes, you may, but you're right, it's dumping the maximum I squared R load to the thing, so you maybe need to cool the motor, okay, to operate there. Sure. Right, so remember that torque profile I showed you for the single coil? Now when you have multiple coils like what's going through here, each one of those coils has a little kind of a ripple. So the overall effect is, it's kind of like almost like a constant torque, but there is a little bit of ripple in it. It's called torque ripple. Okay, and based on the construction of the motor and all that, you will see that torque ripple curve. No, this generally applies to what's going on with the motor. So, sort of looking at what happens with torque and speed. Okay, so another thing to notice here, let's suppose I'm at a particular torque, right? And I've applied this amount of, at this voltage, say 5 volts, and I'm at some speed. Okay, so if the torque stays constant and I want to get to a higher speed, what do I need to do? I need to increase this, which basically at that same torque will move me off to another torque speed line, right? Now I'm at a higher speed. So the way I'm going to increase speed for a motor, given a certain torque, is I got to increase the voltage applied to the motor. Okay. Okay, so we looked at stall torque, no load speed. The slope of this line, okay, sometimes you'll see it in the data sheet called the speed torque gradient. You know, gradients are slopes, and it's speed torque slope. Okay, speed torque slope. And again, when I said that if you express in SI units, these two values will be numerically the same. Okay, if you do it in other units, they won't numerically be the same. SI. Okay, so that's kind of the torque speed behavior for a pneumatic motor. Now let's talk about power and efficiency. Okay, so power. So if you take that relationship that we have for speed, output power from the motor is E times torque, right? Power E times torque. Okay, so if you run through the numbers, here's the relationship for power out from the motor. Okay? So that's power, the function of torque, okay, by voltage, and the construction of the motor. Now, find the maximum. Where does the maximum power occur, okay, on this sort of torque speed curve? Well, take the derivative of power with respect to torque and set it equal to 0, where that thing reaches its maximum, right? You do that and solve for the torque value where that goes to 0. The curve is right here. Right? You can see here's the power line. Okay? With the inverted parabola right there. Half of either the stall torque, which is also half of the no load speed for that particular voltage applied. That's where you have maximum power out from the motor. Okay, so you buy a motor, and it's like, hey, I want to get the most power out of it, gas power, drive it at half the no load speed. Okay? Yeah, should be. Well, let's see, the video of the okay, the linear relationship, so it should be half. Okay, about half. All right. Okay, that's what max power maximum. Now efficiency is different, right? Efficiency means the ratio of how much power you get out versus what you put in. Okay, if you run through that calculation, okay, with three sides for power out, right, 4 times speed. Power in is voltage times current. What I'm applying the terminals and the current. Okay, run through that calculation, and you'll find something like this. The maximum efficiency, something like this. Here is the efficiency curve. Okay, so this one has a peak around here, and that's higher, it's closer to the no load speed than the maximum power point, which is halfway. Okay, so it's, up here somewhere in speed, so it's closer to the no load speed. So if you were, say, operating something with batteries, if you had to make the most use, right, not waste power, not waste the energy from the battery, you probably want to operate the most efficient point. Okay? And so the trade-off is you're not going to have as much torque, right? Now, if you can trade off both, you could maybe operate somewhere between those two, somewhere that we're fairly efficient, right? If you get as much power as you can, you probably want to be operating somewhere in there, okay? It's going to be sort of, somewhere in here.
four different things on the y-axis. And it corresponds to the wait, we'll just get so there is a correspondence. There is a relationship between the power and the that's not even graph four different values versus the y-axis. Right. Yeah. We're flat. The speed versus the power. Yeah, well, this is all part of effective torque. Okay? And if you look at on the torque speed line, right where it's going to be, it's halfway, right? Halfway between like lower. It's not that's not that graphic probably so this is correct. However, the torque, the only thing correct about that is that the four graphs is on top of each other with no scale. Right, they're all with respect to the torque. So long as we, pick off the right numeric value, we're good. Yep. Do generators have a graph? In terms of efficiency and power? I think so. Yeah, because in a sense it's sort of operating in reverse. Okay, so since we're if you look at a lot of the motors that you can get out of the catalog, those no-load speeds are relatively high compared to stuff that we want to do at sort of speeds for manufacturing. So we're often going to need to gear down the motor, okay? And so you'll find the motor manufacturers will sell motors that also sell gearheads, okay, to drop the speed into a range that we can do something with, okay? And so here are sort of two flavors of gearheads. One is spur gears, okay? So you've got smaller, larger gears and mesh. The other is a planetary arrangement, okay? Where you've got the gears operating on a sort of planetary arrangement. So they'll have different sort of capabilities in terms of speed and torque output, how quiet they are, things like that. So those are some things that you have choices for. And I've got just a bunch of motor manufacturers kind of curves in here so you can actually see how they plot out realistically for a given kind of motor and what you can do from that determine some of the current torque values that you might want to use to drive the motor to get you're talking about. Okay, so here's another typical motor. Okay, here's the speed, here's the torque, okay, and then here's the efficiency line, here's the current line. Okay, questions so far on some of the motors? We now know how they operate with their torque speed characteristics. Let's go on and start talking about how do we control these things, okay, and how can we size them for our use. Okay, so talk more about this, how to control bidirectionally, and talk about servos, and then we'll talk about motor sizing. Okay, so there are lots of other actuators. We'll cover a few of them here. Talk about servos. All right, so in addition to that kind of motor that's going around, which we call a brush-type DC motor, there are brushless. Okay, so that commutation, that basically switching the current through those coils to keep it rotating, and those serve through that commutation range. Well, there are motors that don't have any brushes. They're called brushless motors. And so different construction. So here you have the rotor, and this time we've got the magnet. Instead of being on the stationary part, they'll often be mounted to within the rotor system. And then we'll have a winding on the stationary part, like that outer ring. Okay, so what happens is the coils on the outer part will create a magnetic field that these magnets want to align to. So you can magnetically or electrically move that magnetic field around this ring. These magnets want to follow it. Okay, so instead of being sort of mechanically commutated like with the brush type here we use some sensors, small sensors, which we'll talk about in a little bit, that sense the angular position of this rotor, and that information is then used to drive the transistor to cause that magnetic field in the stator, the stationary part, to rotate. Okay? Based on where this is, it will cause it to rotate. So, all we have are bearings that hang on to the shaft. If there's no other physical contact, these small devices are actually separated away from this entity. There's no physical contact, so that has some really nice advantages. Okay, so we do a commutation electronically rather than mechanically. So since nothing's rubbing like on those commutation segments, there's no wear. Okay, so these permanent motors, after a while, those brushes wear, and that's a problem. Maybe you have to replace them or replace the motor. So, since there's no brushes, there's nothing to wear out, so those two things can be used for a long time. Also, high speed. You really have to go up to high speeds in a DC motor. You're probably going to be using a brushless motor. And that's also because of this commutation. What will happen is with these brush type motors, you can be going so fast that that commutation that springs will basically miss contact. You basically jump over these and not make contact. So that's a problem with high-speed commutation. Also, with wear. The faster you go, the more wear you're going to have on the brushes. Okay? And so there's some limitations. There's also noise, right? You have this contact all the time. That rubbing actually produces mechanical acoustic noise and electrical noise. Because every time you jump the segment, remember the current flowing in a wire that has lots of inductance, and it doesn't want to stop when you break across the commutation segment. So you get into a spark because the voltage goes up. There's that current flowing until it can dissipate. And when you get sparks, that creates electromagnetic noise, it's radiation. Okay? The whole time the radio is using these spark generators to create the electromagnetic radiation for propagation, radio propagation. It's a huge thing for generating these sparks. You see really?
I've seen a couple. Yeah, they're pretty electrically noisy.
So these don't have that. So they're electrically quiet. So for real precision applications, you see brushless motors. And then because you can just get rid of a lot of the steel and you just have the magnets here, the inertia of the rotors for brushless motors can be kept pretty low. So you get really high performance and you're able to change speed higher in these kind of things than the brush type. Okay, but it's a little more complicated to commutate, right? And I've got to actively do it. Okay, so more complicated control, so it's got more electronics, they tend to be higher cost. Now you can take this kind of motor idea and you can essentially unroll the rotor and the stator and get a linear motor that will operate on the same principle. Okay, so here are some linear brushless motors, okay, which has, in this case, the magnets are on the stationary part, and the coil is in this movable part, okay, we'll move back and forth. We'll get to talking about stepper motors later, with linear version. Here's actually an XY version using step. Okay. So, the nice thing about these are you don't have to have any steering. You can drive things directly to the really high accelerations with no backlash to the gears. And so you see these on really high performance, high precision systems, especially on semiconductor equipment manufacturers using the motors to stages around lithography and things like that. some of the higher performance machine tools are going to be used for high acceleration on the axis, okay? And no backlash to like ball nuts and things like that. But they tend to be more expensive on the rotary type systems. Okay. So, maybe one more slide and we'll switch. So you can use motors that will create rotary motion to also create linear motion. And a very common approach is, say, a linear actuator. We take a motor, take a screw, this time very sort of coarse, a lead screw, and a nut. Okay, that can basically translate along as you rotate this thing, right? You move along depending on direction. And if you couple something to that nut, you can have that motor basically translate something back and forth. Okay? And then you can, get those package up systems where you've got here the motor, and kind of a belt of gearing. Okay, got these screws in here with a nut. This will cause the shaft to move in and out. So linear actuators, you got them in pretty small sizes. Okay, so those are some possibilities. Okay, so I think what I'll do next time, I'll bring you the stage that we'll take a look at. So, we'll talk more about actuators.